Hello and welcome back to Calculus 1, section 3.11, there we go, on related rates. So the goal is to learn to solve particular type of application problems, you would call that word problems, where we get to measure some quantities, calculate others, so we can understand the nature around us. So first we talk about the title. We have the word rates, and we know that dy dx is a rate. It's instantaneous rate, and this dy dx is a general rate that we use to understand mathematics. Once we start applying this to problems, to word problems, these variables change, and they take the letters that would describe the quantity that we are observing. So one of those is t, which stands for time. Now, time could be measured in minutes, in seconds, in hours, in years, months, whatever. So we all understand the concept of time, which flows right to the positive direction. And in section 3.11, everything will be measured in respect to time. So to understand what we are going to do, we can consider an ice cube left somewhere in the sun, and the ice cube has the side A. All sides are the same, and we can write the volume formula of A cubed, which is when you multiply all three dimensions together, and volume represents of how much of the cube there is on this one pile. Now, as it melts, the ice changes its state from solid ice to liquid water, and then the water flows away, right, leaving the ice cube smaller and smaller and smaller in time. So what happens in time is that the volume of the ice cube is less. Each side, each edge of the ice cube is less. The surface area of the ice cube is less. The diagonal of ice cube is less. So all of the attributes of ice cube are decreasing in time as the ice cube melts. And if we want to consider the volume, we can calculate these things. Now, collected all of the water that was melting and so on, did some conversion and so on, and actually did the experiment to the reasonable accuracy to show that this concept actually works. Now, what can we measure? Well, if I have a volume equation, I can take the derivative in respect to time, and this is where our implicit derivatives kick in, because I have to now take the derivative of v in respect to t and take the derivative of a in respect to t. Remember, v is volume, and the volume is changing because the ice cube has less water there, and the length of the side, the edge, is also decreasing because, again, ice cube is getting smaller. So now, when I take the derivative of v, I will get 1 multiplied by dv dt, which is the chain rule part, which we said I took the derivative of v in respect to t. So this is the same as dy dx for improper integrals. On the other side of the equation, we have 3a squared and then dA dt. Now, we don't really need this 1 times, so I'm just going to get rid of it. This equation here is called related rates. You have two rates present, and we understand these rates as the first one over here as the rate of change of volume in time, and the second one, and just put in time over here so I have more room for the other side. And on the other side is the rate of change of side in time. So we have two rates, and they are related through this equation, right, with 3a squared. So now, as I said, as engineers, you have to work these things out in some cases. And when you look at this, you would say that on one side, you can either measure the change in volume or you can measure the change in length of the side. It depends on what is convenient to measure, and then this equation will calculate the other rate that you need. Now we'll put this, obviously, melting ice cube is nothing special, right? We're going to put some of the applied examples that actually make sense and see these things at work. Now it's important to talk about units, because units are the ones that reveal information that you have and what you're looking for and so on, because in some problems it will not be explicitly said that you are looking for dV/dt. The wording that it's used is the one that helps you decide, and then in some case the units that are given helps you decide. So first of all, units. So length is just meters or feet, so on. Area is going to be meters squared, feet squared, inches squared, and so on. So those are squared. Volume is going to be meters cubed, feet cubed, inches cubed, centimeters cubed, and so on. So now, if I say, given 4 meters squared per second, that's enough for me to know immediately what this is, just because of units. What is this? Meters squared represent area, but you have like a whole bunch of other stuff there as well. So what is all together? What kind of quantity does it represent? Okay, let's start here. What is this? Okay, good. Now, division means what? Yes, what does it mean to divide? What is it? It's a ratio, it's a rate. Okay, good. So what is this rate? What is this rate when you're looking at the units? And this is a crucial skill. Once you figure this out, the rest of the section is a joke. You know it's a rate, you see meters squared, you see a second. So what is the rate? This is what rates look like. We talked about it already. So, what rate is this? D8, finally, thank you. Change in area in time. That's what it is. Let's say given, so dA dt equals 4 meters squared per s, right? Say given radius, and then let's say 6 inches per second. What is this? Okay, we'll use dr because radius is r. dr dt. It's a radius, a rate, because it's a rate because you have 6 inches per second. So inches per second. If you just say given radius 6 inches, then r equals 6. That's all. Inches. Because when you have inches per second, that means there is a progress in time, there is motion, and this radius is covering 6 inches per second in terms of a growth. Given radius 6 inches, well, that's just a length of 6 inches. There is now no progress, no change. Because there's no time for this growth to happen. It just goes and it's steady. So all rates in here are presented as derivatives. And we just go from there. All right, so let's take a look at some of the applied problems to make sense of all of this stuff. And I think one of the cool problems would be the oil rig problem. I think that's the one that, yeah, whatever. So here's the oil rig. I'll put as OR, right? And then there is some kind of problem with the drill, and then it starts leaking oil into the ocean, #BP, right? And the oil starts spreading around in concentric circles. We know that oil and water don't mix, so oil floats on top of the ocean, and then it keeps spreading. So now you see that you can actually compute the rate of spread of this oil on the surface, right? And this becomes now environmental application. What do you want to do? You want to call the cleanup crew as soon as possible. They need to know what kind of an area they are working with, and you can compute how fast the area that needs to be cleaned is growing. So if we have a problem like this, I'm just going to steal the numbers from the book. So if you have a problem like this, they would say an oil rig springs a leak in column C's and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at the rate of 30 meters per hour, if the radius, right, so we have the radius which keeps, right, growing. The radius keeps growing as the oil spreads, and more area is affected by this oil leak. So it says radius increases at the rate of 30 meters per hour. 30 meters per hour. what do I get to write as my mathematical notation for the problem using this sentence? What piece of information is given to me? Of what? Good. Rate of change of radius in time. So we have dr dt. Rate of change of radius in time is equal to 30 meters per hour. Another sentence says, how fast is the area increasing? How fast is the area increasing when the radius is 100 meters? All right, so how many pieces of information do we have in this sentence? I'm speaking English, right?
The radius is 100 meters.
Okay, r equals 100. Good.
They want you to find the area, like how fast the area is increasing.
Which means what they're looking for?
At the rate.
Yes, the rate of change of area, dA dt. So 2 pieces of information. So the first sentence says radius increases at the rate of 30 meters per second, so dr dt is 30. And now they say, how fast is something changing? How fast is something changing? It's always going to be d dt. How fast? How fast is the volume changing? dv dt. How fast is the area changing? dA dt. How fast is the radius changing? dr dt. How fast is the height changing? dh dt. It's always the word fast is also the word that we use to describe the rate. And then when radius is 100 meters, that should be clear. Radius is 100 meters, r equals 100 meters. So that's the one. So these are the 3 pieces of information. When you read a problem, you should be able to locate these quickly. That's it. And now you ask yourself, what kind of geometry do I have, which governs which formula you're going to write. You differentiate, plug in, and you're done. So what geometry do we have of the problem? Area of the circle. Perfect. So you ask yourself, what is the geometry? Geometry is a circle. What do you want from that circle? Because you know about the area, you know about the perimeter, right? You know about the radius, you know about the diameter. So what do you want from a circle? So it's not enough to just know, oh, it's a circle. But you also want to know what you're looking. And that is the formula for the area of the circle. What's the formula for area of the circle? Pi r squared. Great. And we are going to differentiate that in time to create our related rates. Derivative of a is 1, followed by dA dt. On the other side, we have 2 pi r, right? Derivative of r is 2r. So 2 pi r, and then we have dr dt, because we took the derivative of r in respect to t. We have to follow with the chain rule. We learned that in 3.8. This formula here is called related rates. And that's the formula that you will be using as engineers to figure things out. Now, we can use this, obviously, in business and economics. We can use this in engineering and so on. So we'll see a whole bunch of examples as we go on. So the next is to plug in all the numbers. Well, we are looking for dA dt, so we leave that alone. 2 pi r is 100, and the r dt is 30 for 6,000 pi meters squared per hour. So area is changing about 18,000 square meters an hour. 18,000. Pi is about 3, right? So 3 times 6. 3 times 6,000 is 18,000. 18,000 square meters, is that a lot or not a lot? 18,000. 18,000 sounds like a big number, right? It is a lot. It is a lot. So now, right, it's time to panic because you calculated. Now this calculation, this is one of the simplest problems you can possibly see. Right, this calculation should take about a minute or two, and you present your dear company with a horror, so they can panic, and start taking measures as soon as possible. So far, we have seen the ice cube problem, where we differentiate in respect to time to see how fast is the volume changing in respect to how fast is the size changing. The second example with the circle, we again differentiate. We will always differentiate in respect to time in this section because we are looking for how fast the stuff is changing, and fast is obviously happening in time. So we have to take derivative every time, every problem. We take the derivative in respect to time to make sure this works. Let's see another problem. So we have an airport over here. And now there's an airplane flying towards the airport from, well, the airplane's going due west, but it's coming from east. And then there's another airplane going up towards the airport. What are we trying to achieve? Well, what is the goal? The goal is for this. Exactly. The goal is for them not to collide, right? To land safely. That's the goal. Now, if two planes are to collide, what's the distance between them? 0, right? So I have this distance here, call it the distance d, that we can compute at any time if the distance x and distance y are given to us. What is the geometry? What is the formula that takes care of these lengths and stuff? Yes, Pythagorean theorem in the right triangle. So Pythagorean theorem in the right triangle is the formula, the concept that we would use to calculate this d. But see, the trick is that these airplanes are flying. They're flying at certain speed. We can pick some numbers from the book and see what those numbers are. So when you are looking at these, the closer both airplanes are to the airport, the shorter the distance between them. And we need to track that capital D, because we don't want that capital D to be 0 ever between any two given airplanes. So now you suggested that we should use we should use Pythagorean Theorem. So let's write the Pythagorean Theorem, which is x squared plus y squared equals to d squared. So this is what we get from geometry of the problem. We understand that there are two planes flying towards the airport. We understand that they're not supposed to collide. We understand that this capital D should never be 0. So once we have the geometry, we have the concept, then we can write the formula down, and now we will differentiate that formula to, we differentiate the formula to see what is the related rates formula, the model. Derivative of x squared is two x. Dx dt, exactly. You took the derivative of x in respect to t, so there is a chain rule, dx dt. Okay, what's the derivative of y squared? There we go, perfect. And then what's the derivative on the other side? d dt. Nice. There is your model. Well, when you kill these 2's, now you can divide these 2's, and you have x dx dt plus y dy dt is equal to d dd dt. So look at this formula. Does the formula make sense? What are these things that are in the formula? What do they represent? What is x?
X is the top plane's
Distance, very good. So x is the, okay, we call it the top plane, fine. Top plane distance. And what is dx dt?
The rate at which the speed.
The speed of the top plane, nice. Speed of the top plane. Great. What's y? Distance of the, yes. Distance of the bottom plane. And what is the speed? Speed bottom. And then what is d now? I'm going to put these in red. What is d? Yes, great. Distance between two planes. And then what do we have here? What is dd dt? Yes, the rate of the decrease of their separation, right? So, rate of separation. Rate of separation of planes. That's what we have. Perfect. So now, when you read the problem, it says, two small planes approach an airport, one flying due west at 120 miles per hour. So this one due west travels at 120 miles per hour, and the one that is going due north is 150 miles per hour. Assuming they fly at a constant elevation, how fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles away? How fast is the distance between the planes changing? So what are they asking for? dt. That's the distance between two planes. Distance d is the distance between two planes. They want to know how fast is that changing, because if it's changing quickly, the two planes are approaching each other quickly. If they are on the same elevation, obviously, it's going to be a near miss. If you use logic. They use near miss wrong, right? Does it make sense? Near miss. That's a collision, near miss. Near hit is when they miss each other, actually. Does it make sense? But think about it a little bit.
So you almost missed it.
Exactly. You almost missed, but you didn't. Yeah. Oh, it was a near miss. Really? But then again, we drive on a parkway and park in a driveway, so it makes sense. Anyway, so let's go and see all of these values. We already have the numbers, right? I have that x is, I have the x, I have the speed for x, I have y, I have speed for y. They are looking for dt. The only thing I don't have is a capital D. That's the only thing I don't have. Everything else is given to me. Oops. So x is 180, dx dt is 120, y is 225, dy dt is 150. They are looking for dt, so that's what I'm looking for, so that stays the way it is. The only thing I don't have that I need to plug in is capital D. How do I find capital D? Pythagorean Theorem. Right here, you have equation that connects x, y, and d. You can use x and y to come up with the value for d, and then you plug that in as well, and then you can calculate what you need. So, need capital D. And that's going to be x squared plus y squared equals to d squared, from where d is equal to square root of x squared plus y squared. So, d is the square root of 180 squared plus 225 squared, and then you use your abacus to figure things out. So we have 180 squared plus 225 squared, and then the square root, you get 83,000, blah, blah, blah. Square root of the answer. Keep one decimal, 288.1. And now we can plug everything in related rates. Now we have to be very careful the way we plug these numbers, because we need to get correct values. This is applied problem, so signs matter, and signs matter in terms of the physical case that you have. So I'm going to plug in x as 180. Lengths are always positive. If you live 10 miles away from RVCC, then RVCC is 10 miles away from your home. Yes?
On a test, would you want us
you are allowed to go one decimal past the numbers you have. So if your numbers are integers in measurement, then your calculation can allow for an extra decimal place. So I rounded because there is 4. There are a whole bunch of.
No, meaning like just to 288 because it's 0.1.
What's 21?
Like, what if I wrote just 288 instead of 288.1 since it's just 0.1?
Then your answer will just be
No,
not as good as someone else's answer,
I just didn't know
which
if you
means
wrote
they,
it down.
as I said, then your answer will just not be as good as someone else's, and that's where they beat you on the proposal, and you don't get the job. That's the thing. In science, whatever amount of decimals you can measure, your calculation is allowed to provide additional spot. So if you measure something that it's 28 whatever, your calculation with that 28 is going to come up to be maybe 37.6, right? Even if it comes out to be 37 exactly, scientists would put 37.0. Because the extra decimal place is provided through the calculation, you cannot go more than 1 because your measurement is not precise. In that case, the precision of the measurement governs how many decimals you get to keep in the problem. So the more science courses you take, those things make more sense. Unless you talk about the money, then you always keep 2 decimals because it's cents. And if you talk about people or babies are people still, or puppies or something, you keep integers because you really don't want to have 37.6 if you're talking about babies. Right? But for these cases, whenever you're talking the decimals, you always provide a single decimal place more than that you had for the measurement. So 288.1 is proper way. Now if you put 288, it's a math course. Well, all right, let's talk about importance of signs in problem like this and where the logic, common sense have to kick in. If you just place all of these values, just dump them into the problem the way they are, you are going to run into trouble because the values for speed need to be negative because the distance to the airport is getting smaller. So you are going towards the airport, and because you are flying towards the airport, we are going to have negative 120 over here, plus 225 miles for y, and then negative 150 over here, which is equal to 288.1. Again, lengths are always positive values. And then you're going to have your dd dt. So we have to put negative values. And this is now the rule of thumb for entire section. When the quantities are decreasing, I don't care if it's a length decreasing, volume decreasing, you always use negative numbers. When the quantities are increasing in terms of rates, you always use positive numbers. So the airplane is going towards the airport. The distance of the airport and the plane are decreasing, therefore it's minus 120. The same thing for the other plane, it's 150, decreasing the distance, right, closing in. So, and when you use those signs, you will get appropriate answer, which would be a negative number for dd dt, signifying that the distance between 2 planes is getting smaller. And that's something that is important. So we have 180 times negative 120 plus 225 times negative 150. All of that divided by 288.1 to give us negative 192 So dd dt is negative 192.1 miles per hour. So the distance between the two planes is decreasing at the rate of 192 miles per hour. So in 1 hour, these two planes would be about 200 miles closer than they were an hour ago. So we have this Would this calculation be important? Is anyone doing this calculation at any point? Two airplanes approaching the airport.
That's what they do in the flight to our airport, right?
People?
What's that?
People?
Yeah.
Yeah? Let's take a look. What does it say here?
Flight track.
Then?
Real-time flight track.
Okay. Canada, New York, Philadelphia, Washington, United States. You think there is a Joe somewhere in the flight tower computing the distance between each of these planes?
I thought you meant like, is it being done? Yeah.
It is being done. Who's doing it? What's doing? Yes, computer is doing this. Now, who's programming computer? You see, this is where the computer science geeks kick in. They have to write the code that will, using linear algebra and calculus, track 15,770 planes in the air, currently displayed on a screen 1,500 out of 15,000. Okay, so this is 10% of all of the planes that are currently tracked, and this is just people planes. They do not track military aircraft. They do not track all of the diplomatic, like, you know, Air Force One and so on. This is just commercial flights. And you can pick any of these planes, and it will give you all of the info left when it's landing and what it has. And then if you actually sign up and pay for the website, they also give you the 3D view. There is a camera on the bottom of the plane, so you can see what you can see from the plane too as it flies. For every plane that it's in the air, that's really cool. Now you get to see just a little snippet of what it is to untangle this mess. And we did the calculation for two-plane interaction. It's different when you have, you know, about 100 planes hovering over your airport on different altitudes, making sure that they all land safely, and then all of the planes that need to take off safely. So if we zoom in to New York, just to see the amount. I mean, if you see Allentown and Easton on this map, you know. Right? So there's your JFK, there's your Newark airport. You can't even tell, right, of how closely. Right? You really have to zoom in to see what is going on. And LaGuardia, right? So 3 airports in one. That's a lot of planes that you have to track, right, using the software. as I said, computer science, people that write this, they're hundreds of thousands of dollars. Some of the computer science jobs, entry positions are 100K because they provide software for stuff like this. It's not humanly possible to track this stuff.
No, I know.
Which is why their salaries are, and then you have all the security stuff and networking stuff and whole bunch. So you can actually find entry-level positions for computer science after graduation at 100 to 110K. Then the next step would be usually chemical engineering at 80K. The people that are watching the screens, they're just technicians. They are not computer scientists. They are not. So computer technician. Now there is a lot of jobs in air industry, but again, shortage of pilots is coming up too. So that's going to be another area for people to consider. Each one of these planes has a pilot and a co-pilot and usually a third person if it's large enough plane.
Doesn't it take a while to become a pilot, though?
Do what?
Doesn't it take a while to become like a commercial pilot?
Yes. Just like it takes a while to become a surgeon, because remember you have 350 people on board, right?
It can eat like
And each plane can be a missile. We know that too.
No,
you need
So
100 hours of flight time. Like
1,500 for the commercial. 1,500. You have to get, if you want to fly the two-seater plane at the airport in Hillsborough, right? That for that license you need 300 hours or something to get through, to get just the basic license to fly a two-seater.
when you start off,
With a two-seater. Anyone in this classroom has enough mathematical knowledge. Math that you need for this, guys, is pre-calculus 2, trig. Those are the types of problems that you are going to see on pilot exams. If you are able to do trig, you are able to pass math that is on exams for pilots. And then you can, and after that, take a while, right? You are going to go to a two-seater, to a four-seater, to a six-seater, to a larger plane. Then you're going to fly packages around. You are going to fly. The only way that you can kind of jump a little bit faster to this is if you go to Air Force and you become a pilot in the Air Force, and then after that you can be an astronaut. But for commercial flights, it's 1,500 hours of logged flight without issues to be a commercial pilot. So there they are, 30,000 pilots and co-pilots, right, flying currently right across, and you know, it's a job, right? It's a job. So you have, and then you have the people in the mission control tower, and they would be staring at the screens, making sure that the computer is giving the right order to land, because the computer has to take account of how much fuel is left, and to assign priorities. So, anytime when you are impatient to get somewhere and to land somewhere, just understand why you are either delayed or why it takes time to take off or land or something. Yes.
And you can like storm delays too, which is like back up to like hours sometimes.
Mm-hmm. Yeah, the storms and the terrorist threats. It's like so many things that can go wrong very quickly, and it's still the safest way to move around and the fastest way for us to move around. Now you can get to the other side of the planet in a day, which is amazing, but takes time. So that's it, guys. That's the related rates for this situation. Let's see what else we can figure out with these awesome related rates. So we have seen the use of the right triangle as a geometry. But as a right triangle, it's not only Pythagorean theorem. What else do we have for triangles? We have area, we have perimeter, we have 6 trigonometric functions if there is an angle inside, and then Pythagorean theorem. So it's not just geometry, but also using, right, your head to think a little bit about what type of the formula is the formula that it's useful, right? And for this particular problem that deals only with distances, the only two formulas that deal with the distances only for triangle are perimeter and Pythagorean theorem. Now, perimeter is just sum of all sides, so that one doesn't really fit. And obviously, none of the trig formulas would work in this case because we have no angles to worry about. And we're not talking about area either. So it's generally by process of elimination. So for any shape, you generally have, a couple of formulas, and then you can reason your way to which formula to use. Now, usually what I like to do is to, before we go to the next problem and make more money, I like to play a video. So we're going to watch a video. Okay, let's see. Would this be a good one? Let's go with this. Can we skip these commercials? How hard is to install the ad block? Come on, guys. There we go. Okay, great. Unfortunately, there is a cutscene, but not this one. This is a good example, but I would like to see the one that is vertical, this one. Okay, so now observe this shot. You think this is a Joe somewhere holding the camera, right? Unfortunately, the Fox News Now over here is covering the two pieces over here. Here is your speed in miles per hour. This rocket is currently doing 1,000 miles per hour. And here is the altitude in miles, so it's about 10 miles up in the air. And I'm not sure why is this upside down, but it's upside down. The shot that I wanted you to see and pay attention to is this shot here. So this one. So this is the shot that I wanted you to see. So let's do some calculations for engineering before we start building stuff. So what do I want to design to capture this shot? I want to design a mechanism that when I have a tripod, let's say it's a tripod right here, the mechanism that will have a servo motor right here that will be able to rotate the camera. The camera will be mounted. There's the rocket. As the rocket goes up, the camera will be turning to make sure that the rocket is always in the middle of the shot, just like the one that you have seen. So now, when the rocket is on the launch pad, right? The camera is sitting at, let's say, the angle 0. And then when the rocket launches, the camera will slowly rotate up and up. And we need to do that automatically. Not having a person rotate and shake, but actually have the motor in the camera. Now, the motor will be controlled by the controller. Controller will be controlled by the computer program. You can use Raspberry Pi for this thing. It's not a big deal. Python programming. to design how much voltage on this step motor you need to add so that you get what we call angular velocity. So this is angular velocity, which is how fast things move in a circle so that the camera is capturing the rocket at all times. So now to design the system, you're going to have some bunker for the camera. You're going to have your launch pad. You're going to have your rocket at the launch pad. The rocket is going to shoot straight up as you, oops. The rocket is going to shoot straight up. Your camera is going to be mounted on that servo motor that sits on the tripod, and the camera is going to take the direct shot, but then as the rocket goes up, the camera is going to take the shot. So no matter where the rocket is, as the rocket climbs, right, the camera will be turning, right, to have the rocket in the middle of the shot, just like the one that you guys have seen in this video. So you can see the progress over here. You understand because you see the numbers. You know that this rocket is going 900 miles per hour right now, and it's still in the middle of the shot. You know how hard it is to even record a video of a car or a motorcycle that it's moving less than 100 miles per hour. This thing is going 9 times the speed, right? So, sure, it's far away, but still, you need to make sure that you are capturing the footage. All right, so I'm just going to get rid of all of these intermediate lines and just keep the 2 lines that I actually care about. So we know that this camera will be turning this way with what we in physics call angular velocity omega, and angular velocity omega, right? So this angle here, the angle is important. We are going to set up this camera, let's say 1,000 feet away or 2,000 feet, or I don't care, all right? So there is some distance between the camera and the rocket, otherwise, right, the launch is going to melt the camera. So you got to put it away. The camera is going to record the rocket, and rocket is going to climb up. I just noticed this line is because my computer is at an angle. So the rocket is going to go straight up, and we have the height h to measure that. So now my question to you is, what is my geometry here? What type of geometry do I have? I'm not asking about a formula. I'm asking about geometry. What shape do I have? Right triangle. Good. Now, what formulas should I consider for this problem? Okay, so you are suggesting trig because there is an angle. Perfect. Which of the 3, sine, cosine, tangent, should I use? Tangent, very good. The values that are given to me are opposite, adjacent, and an angle, and that's tangent. So when I write tangent theta is equal to h over 1,000. It's tangent theta. And now we can write that 1,000 tangent theta is equal to h. So we don't drag the fractions around, it's fine. At this point, I'm going to differentiate both sides. And what's the derivative of tangent? Keep talking. Secant squared, what? Theta. Then I took the derivative of theta in respect to time. What's the derivative of h? Beautiful. You have to have at least 2 rates. There will be problems with 3 and 4 and so on, but you must have at least 2. The height is changing because the rocket is going up. We saw the height changing. There was an altitude measurement, and there was a speed measurement as well. We know the speed and the height of the rocket at every instant of its flight. Great. So now, what is this d theta dt? That's the omega we were talking about. That's the one we want in a design. Omega is d theta dt, angular velocity. That's the one that we want. Angular velocity. Because you want to know how fast you get to turn. And the motor that you put into, like the axle of the motor that will be spinning and turning, right, has a rotation which is measured with omega, which is the spin. So you need to program into the controller, as a computer science, let's say, you have to program the equation that will take the input and as the output provide the voltage that will be enough to turn how much it needs to turn so the rocket is in the middle of the shot. We can actually build this here, right? Math Club I'll propose to Math Club to build something like this so I can actually drag it to class. We can see it. It's simple, but yeah. Anyway. So now I know I need d theta dt alone because that's my omega. Kick everything to the other side. So that's going to be my dh dt divided by 1000 secant squared theta. Oh wait, this secant squared theta in denominator is actually a cosine squared in the numerator. So now omega is equal to dh dt cosine, well, let's put it this way. It's easier if we put, if we put 1 over 1000 cosine squared theta dh dt. All right, we're still not happy because can you really use an angle as an input? You would have to measure that. That's annoying. So how about we see what this cosine is in the triangle we have? So what is cosine in a triangle? No, that would be cotangent would be 1000 over h. Cosine is what side over what side? Adjacent over hypotenuse. We don't have the measurement for hypotenuse. How much is hypotenuse? Pythagorean Theorem, 1000 squared plus h squared. So, cosine theta is given as adjacent over hypotenuse. And I just plug that in. Now you have to square it, right, to replace the square. So omega is equal to 1 over 1000 times, and now I need to square this, so it's going to be 1000 squared divided by, and square will kill the root, and you just have 1000 squared plus h squared dh dt. One of these 1000 will cancel, and you have omega is equal to 1000 over 1000 squared plus h squared dh dt. This is what your job as engineer is, to come up with this equation looking at the situation you have. Now, when you write your code for the controller, you will ask for the input from the mission control or whatever, you would ask for the input with, as you can see, the two numbers that you have. There is the speed, that's your dh dt, and there is your height, h. So these two numbers that are constantly there, and these two numbers that are constantly changing will be live fed into your code, and your code will be computing the omega. Now that omega, obviously, you have the specification for the motor. You will be providing the voltage that will be turning, and the camera would be turning and having the rocket in the middle of the shot at all times, taking only these two numbers into account. At this point in time, the rocket is moving at 11,600 miles per hour. So yeah. And we still can't put it on Mars. This is how sad we are, actually. The way we get them to go to Mars is you make the slingshot with the moon. So you send the rocket into the orbit of the moon, and you use the gravitational acceleration of the moon to propel it far enough. And you have to wait for planets to align. Can't just launch anytime. That's why they have a launch window. Because when you have your orbits, right, like that, you have the Earth. Earth has the orbit with the moon, and then the Mars, and then there is the sun in a focal point right there. You have to wait for them to align like this. You can't have Earth here, and then across from the sun, Mars there, and send a rocket. We don't have anything even close that can do it. So what we do is we shoot the rocket around the moon, slingshot onto the Mars. And we can only do it when they line up like this. You can't do it when the moon is on the other side. You can't do it when the Mars is here and Earth is there. There's only certain part, certain time. Our technology is nowhere, right? As a species, we are really, we are still type 0 civilization. That's if you have a type 0, 1, 2, 3, 4, we are, right, if you use that division, we are type 0 still, with all of the tech we have. Okay, cool. So, but maybe with you, right, it will get better. So now you understand what engineering is all about, right? You create, you draw the picture, right? You see the geometry, and then you just run through the calculation. And once you have the formula, you pick the numbers, the input numbers that can be measured, and you saw, right, on the launch, gives you the speed of the rocket, it gives you the height. You guys know then what you are supposed to plug into the formula to compute. So this omega is change in angle over time, right? So the difference between this and this, right? For my case, the best example that I understood was the clock and the two clock hands you have. You have one going around, which is minute, and it goes around in 1 hour. The other one goes around in 12 hours. So if one goes around in 1 hour, the other one goes in 12 hours, then the minute hand is 12 times as fast as the hour hand. That means that the angular velocity of the minute hand is 12 times the hour hand. So those are the angular velocities. And the angular velocity is 1 in an hour and 12 in an hour. So that's it. Okay, good. What else can we talk about? There are a lot of cool exercises that you guys can. There is a spherical balloon. I love the spherical balloon. So the spherical balloon, those are the weather balloons. They're large, so people confuse them for UFOs, and then they want to storm the army base. Anyway, spherical balloon is going to be inflated, and the volume increases at the rate of 15 inches cubed per minute. At what rate is the radius changing when the radius is 10 inches long? So, spherical balloon inflates at 15 inches cubed per minute. What is the rate of change of radius when radius is 10 inches? Cool. So try this one for about 2 minutes. Geometry is obvious because it's mentioned. We talked about using units to recognize what you have and so on. Okay, let's take a look. We have a spherical balloon. So it's a sphere. And the information given is that it inflates at the rate of 15 inches cubed per minute. So what type of information is inches cubed per minute? Not the volume. Inches cubed per minute. dV dt, change of rate of volume in time. Volume is not the same as rate of change of volume. So you have to be careful about these things. So they give us dV dt is 15 inches cubed per minute. And they give us that the radius is 10 inches. And they're asking us the rate of change of radius, so dr dt. So all of these things are given clearly in words or units. This cannot be made any clearer than this. You have units, inches cubed, that's the volume, divided by time, has to be a rate. Then they say, what is the rate of change of radius? You immediately know it's dr dt because they said rate of change. And then radius is 10. Well, the word is means equals, so radius equals 10, r equals 10. So these are the three pieces of information that are given to us in the problem. And we have to work with those three pieces of information. The geometry of the problem is a sphere, ball. We need to know the volume formula. So volume is 4 pi over 3 r cubed. We are going to differentiate that and have dV dt is equal to 4 pi r squared dr dt. This is your related rates model. You have the rate of change of volume connected to the rate of change of radius. Obviously, everything happens in time. Since the balloon is inflating, I'm using 15. If it was deflating, I would use negative 15. Negative 15 would produce a decrease in radius because you would get a negative number on the other side as well. So because it's inflating, then I'm using positive 15. Then I have 4 pi, radius is 10 squared, and I'm looking for dr dt, which is what stays as a variable. So now dr dt is equal to 15 divided by 400 pi. 15 divided by 400 pi, and you can just say inches per minute. Now, if you are interested in the decimal, you can calculate the decimal for this. So 15 divided by 400 and by pi, which is approximately 0.01 2, whatever, inches per minute. If you are to write this in scientific notation, you would write it 1.2 times 10 to the negative 2. So now the question is, do you know all of the volume formulas? Because you need to know all of the volume formulas. And the easiest way to learn all of the volume formulas is to put them into 3 categories. So we'll do the categories, then we'll do one more problem, and then we're going to take a break. Then we're going to talk about the exam. So this is lecture on volume. Volume will be broken into, as I said, 3 categories. The first category is prisms, cylinders. So you're going to have a cylinder in there, or triangular prism, or your cube. So all of these shapes that are boxy, okay, they will all have the same form for volume, which is area of the base times the height. So B stands for area of the base. So it shouldn't be hard for you to know any volume now. What's the volume of the cylinder? Well, you have a circle on the bottom. Circle has area of pi r squared, and just multiply by height. So all of the volumes for prism-like objects now become simple because they all take the same form. Then you have a second group of objects which I call spiky objects. And those would be the cone, the pyramids. And I don't care if the pyramids have 3 sides or 16 sides, I don't care. Right? Maybe you have the pyramid that has 4 sides, whatever. They go up in a spike. And the spike is going to create the whole group of these objects, which is going to be 1/3 base times the height. Same base times the height like the first group. It's just 1/3 of it. So now you know volume of every pyramid as long as you can calculate the area of its base. If it has a triangle, if it has a square, if it has a rectangle, if it has a hexagon, I don't care what it has. If you know to calculate the way to calculate area of the base, you will multiply by the height of the pyramid and you will multiply by 1/3 and you will get the volume of the spiky object. And finally, the sole object in its own category, the perfect three-dimensional object. Three-dimensional object, sphere or a ball, yes. Its own category, and it's a perfect object because of many, many, many reasons. A lot of applications, obviously. I mean, we live on a ball, we play with the ball, right? And there's a lot of stuff. For instance, here's just, we already had 4/3 pi r cubed. We already had that formula. The reason why the planet is round, like a ball, is because of the physical law that every object tries to exist in the state of the lowest energy, which is also what we try to exist. We all try to be as lazy as possible and cut the corners whenever we can, right? It's the natural thing, right? To be at the lowest energy state. You are sitting. Why am I not teaching this to a classroom of 30 students doing push-ups for an hour and a half? Or sit-ups or chin-ups? I don't care, right? This is the lowest energy state for you right now, so you can focus on things that I am saying. There is one that is lower than this, which is when you're horizontal passed out, right? But you're definitely not going to be learning this while you're on treadmill. So, the lowest energy state, and because all things tend to be in the lowest energy state, and the lowest energy state because of the potential energy, right? Potential energy has mgh. Every particle, every single particle of the planet is trying to be as close to the center of the planet as possible. And you achieve that in a ball. You do not get to achieve that with us. Well, this point here, the particle at this corner, can just move. If it just moves right there, it's going to be closer to the center of the desk than being there. Which is why they all arrange in a ball. And so on. Another reason for a ball right, to be the perfect object would be the heating and cooling of liquids, the heat diffusion. If you want your tea, so I'm not talking about thermos or anything like that, right? I'm talking about just a cup. If you want your tea, coffee, to stay hot longer, you will get a short, fat cup. If you want it to cool as fast as possible, just by natural causes, you will take a skinny, tall cup. Because the heat diffusion is not happening as much when the shape of the cup is closer to the bowl, right? But when it's skinny, it's more surface area, more heat exchange, and it cools down fast. So these are the things that we are going to do for the volume. You have 3 categories of shapes, and now you know all of the volume formulas. If you are able to calculate the volume of the base, you will multiply that by the height. For spiky objects, you will multiply by 1/3. And in its own separate category, you will memorize the formula, if you don't know it by now, for the volume of the sphere. And any of these would pop up on the exam. So you have the area problems, you have the volume problems, depends on what geometry you have. The last problem we are going to discuss is another engineering problem, and then we're going to take the break. For this engineering problem, we are going to have a conveyor belt over here, which will deliver whatever goods. So it can deliver corn, it can deliver sand, it can deliver gravel, I don't care. The stuff is coming in, and it's going to fall down onto what kind of pile? What pile would it form? Would it form a ball? It's not. Well, triangle is not a three-dimensional object. We have to use a three-dimensional object. Pyramid is close, but it's not exactly pyramid. It is
Triangular.
cone. The stuff is going to fall onto a cone. It's going to form a cone, and the more stuff you send, the cone becomes taller and wider, right? And you get more and more stuff on the pile. You are charged to design a circuit. Hello, electronics and computer science again. I mean, you can't do anything without programming anymore. Don't kid yourself. I don't care what branch of engineering you're in. So now you have to design a shut-off switch, because you can't really use, in these conditions, photo sensors or infrared sensors or anything like that, because there's a lot of dust. There's a lot of dust in these quarries and farms and so on. So the sensors get quickly dirty and dusty, and then they don't work, because the sensors of that kind work on being interrupted. And obviously, as soon as they get dirty, they get interrupted. So you can't use those. And do you really want to hire someone to sit there and observe the pile getting longer, bigger and bigger and bigger, and then maybe 2 or 3 times a day just push a button to turn off the machine, right? So you are designing automated circuit that will shut off the system, and the system, right, and the shut-off system obviously would depend on the change in height of the pile. So you do have a height of the pile, but because the stuff is constantly coming in at whatever rate, that's where you get to use this. And I say stuff, gravel, corn, sand, I don't care what it is, right? Could be Legos in a factory, right? Just bunching on a pile. So what do I have? I have stuff coming in. stuff coming in, falling over here at the rate of dv dt. I know what my production output of the machine, that it's either harvesting corn or it's grinding stone or whatever. I know what the output rate is. The output rate of that machine is the dv dt of what is falling onto the pile. The cones that I am observing on the pile over here will have the radius r and will have the height h. But they will also have, and they both change. The more stuff you put on the pile, the wider the pile and the taller the pile is as time passes by. We want to make sure that the machine will shut off before the cone reaches the conveyor belt, because if the cone reaches conveyor belt, the stuff will fall onto one side of the cone. It will accumulate on the conveyor belt, and it will eventually break. The weight of the stuff on the conveyor belt will break the conveyor belt, and those things are very expensive. Typical recycling plant would have elaborate contraption of conveyor belts to take the paper one way, paper and cardboard one way, bottles on the other side. That sorting machine is $1 million. I mean, we are not talking about $3,000 thing. It's very expensive to have these systems in place. So once you have this, you say, oh, well, the volume coming in, I have radius and the height, so yeah, I'm talking about the volume of the cone. So geometry is volume of the cone. Great, let's use that. Volume of the cone is going to be equal to, it's a spiky object, 1/3 base times the height of the cone. The base is the circle, so that's r squared pi, and I have the height of the cone. Awesome. So now I know that the volume is pi over 3 r squared. You can use lowercase h if you want to, doesn't matter. So this is the volume of the cone. And as I said, it's just way too much to memorize every single one. It's much easier to just remember the general classification and then just use the basic knowledge of areas rather than figuring everything else out. So now that we have this, we are going to take the derivative in respect to time and have our dv dt to be pi. Hold on. Radius is changing, height is changing. What does that mean? Do they look like they're inside? You are thinking in the right. You're thinking the right stuff, but you're saying the wrong thing. So we have two variables. What does that mean? Product rule. Radius is a variable, height is a variable. They are changing, so we need to use the product rule. So for the product rule, copy the first, dh dt, derivative of the second, plus copy the second, times derivative of the first, dr, 2r dr dt. This is your related rates formula. So dv dt is equal to pi over 3, in parentheses, r squared dh dt plus 2rh dr dt. So this formula here, oh, come on. This computer is too slow to get the information that I wanted to use, and then it catches up and goes ahead. This is related rates model. So this is your related rates model. What do I want to know? Well, I want to know how fast is the pile rising. That's what I want to know. I want to know dH dt. I don't care how far to the sides it goes. I don't care. I have all the space to the side. The question is how fast it's going up, because I want to make sure that I shut it off in time before, automatically, shut it off in time. And I can't use sensors because of the dust, right? So now I know dV dt. dV dt is known to me because I know the output of the machine that it's putting stuff on the pile. So output of that machine is my incoming volume of stuff. And I said I don't care whether it's corn or gravel or Legos, whatever it is. There are certain things that I can measure. I can measure radius, I can measure height, right? Those are the things that I can observe. I really can't deal with this dr dt, and I don't need it. So this is where extra geometry, this is one of the kind of spicier problems. We would put this into like a level 2 spice. They have some awesome stuff I'll show you in the book that if you really want to challenge yourself and check your engineering aptitude, those are the problems that you should try. But this one is kind of spicier, on a spicier side. When you have the cross section of your cone, that cone was smaller at some time. So that cone was first above that line, and then it became bigger and bigger and bigger and bigger. Now I know that the cone should rise to the top, but we can also just add the stuff on the bottom. Mathematically it's the same. So now you extract this triangle here on the side, and you see that you can use similar triangles. So this is your changing radius r and your changing height h, and these are the capital R and capital H, which are the ones that you can always measure. You can have the measurement marked on the floor, which will tell you the radius because you would have the measurement 1, 2, 3 in feet, right? So you can just look at the floor and say, oh, it went to the 6th tick mark. It's labeled with 6, so 6 feet for the radius. There is a ruler on the, maybe there is a stick that it's a ruler in the middle, right? And then the whole stuff falls around the stick. So you can always tell the height, you can always tell the radius. That's not a problem, right? So you can use similar triangles to say that the height to height is radius to radius, and you want to get rid of the little radius. So little radius is going to be height times r over h. Now, these two quantities, we know this. We know these. And we know them because we can measure them. So now, what you have is a relationship r over h. It's a relationship between r and h. And you can differentiate that one as well in terms of time to come up with a formula that will eliminate the unwanted rate as well. R over h is a constant, you copy that, and you have dH dt. So now, plug in. So your dV dt now is going to be pi over 3, and you have, instead of r, you can put, so instead of r squared, you will have r over h squared, and you have your dh dt, which is what you are looking for, so that's all cool. Plus, the second term was 2rh, so 2, we don't like r, so we'll have r over h times h, and then there is then h from the problem, and then dh dt is another rh dh dt. Now this one is a little bit convoluted, so I'm going to put what's what. Well, 2 is 2, that's easy. This puppy over here is r, that's same age you had, and the whole thing over here used to be called dr dt. So we just plugged in to replace them from the old equation. And now you just collect the like terms, and you can just plug numbers and you're done. So over here, we have r over h times h squared dh dt, plus, now what do you have? R times r, h and h, so you still have r over h squared dh dt. Oh, there's a 2 in front. You can see that there is h times h is h squared, r times r is r squared, h times h, capital H times h is h squared. So you have the same quantity, it's the same term, so it's 3 of them, right? So now you have dv dt is pi over 3, and then you finally have, I don't need the parenthesis now, I just have 3 r over h squared dh dt. 3 will cancel 3, and you have your dv dt to be pi times r over h squared dh dt. So this would be your related rates model to calculate. Apps.